Or said another way, it's not just matter that falls in a gravitational field, it's light that's going to fall as well. All right, so this is very profound because we're used to thinking of light as always traveling in a straight line. In fact, in construction, laser beams are often used to define the straightest possible line. So there are two different ways you can think about it. You can just, give up this notion that light travels in a straight line, and you could say, okay, I guess if there's gravity, then light curves, and that's the end of that. Or if you're Einstein, you can take it one step farther, and you can say, no, in fact, light is still traveling in a straight line. It's space that's become curved, and in fact, it's space-time that's become curved. All right, so what exactly do we mean by this? So we can imagine the following. So suppose we're here in New York, and we want to, get to Stockholm, Sweden, to see the Nobel Prize ceremony. And we want to get there in the shortest amount of time, which means that we're going to take the shortest possible distance to get there, right? And we can equate this notion of the shortest possible distance with being equivalent to the notion of the straightest line to get there. So certainly on a flat piece of paper, if I have 2 points and I want to draw the shortest line between those 2 points, that's going to be a straight line. On a sphere, though, we know that the shortest possible distance to get, say, from New York to Stockholm is going to look like a great circle that goes around, say, the diameter of the Earth, like so. So to get from New York to Stockholm, I'm going to follow this shortest possible distance. But now, if I were to take this map of the Earth and I would project it out onto a flat surface, so say New York is here, and Stockholm is over here, this thing that I'm calling a straight line no longer looks straight, right? It looks like a curve. So when I was on the sphere, it was clear that this was the shortest possible distance between these 2 points. But if I take this line and I project it out on a flat piece of paper, it looks curved instead. It no longer looks like a straight line. And this is what Einstein argued is essentially what's happening with light. So because in fact it's space-time that's becoming curved in the same way that the surface of the Earth is curved, we need to change what we mean by a straight line. And if we really refer to a straight line as the shortest distance between 2 points, then light is still following the shortest distance between 2 points. Does that make sense?
Yes.
Yes, okay, very good. All right, so what Einstein concluded is that in fact, gravity curves space-time. And light is still following straight lines in this curved space-time. All right, so you can formalize this notion. And so what the math looks like that describes precisely this notion is what's known as Einstein's equations. And these take the following form. So we always write these in terms of tensors. And the simplest way to write this tensor is it looks like a g subscript mu nu is equal to 8 pi g with a t subscript mu nu, like so. All right, so this is the mathematical expression that represents this statement. But what you really need to know is the following. So the right-hand side of this equation, the t mu nu, this is where we input the matter. So we say take a planet, or we take 2 protons like we did at the very beginning, and this is the input into the equation. So the right-hand side of the equation is the source, and then the output is the left-hand side of this equation, which is the g mu nu, and this is what's telling us how the matter curves space-time. So the g mu nu is giving us the curvature of space-time. All right, so very schematically, these are what Einstein's equations are telling us. All right, so these are remarkably well-tested equations. So there are a huge number of precision tests everywhere from tabletop experiments to cosmological observations that verify Einstein's equations. So I should note by saying too, Newtonian gravity isn't wrong. It's just limited in what regime it can be applied to. So we can think of Newtonian gravity as being a good approximation to general relativity as long as objects are not moving very quickly or as long as gravity is not very strong. But as soon as things start to move quickly or as soon as gravity becomes very strong, that's when you need Einstein's general relativity, and that's when you get corrections to the original Newtonian law of gravity. All right, so let's just talk about some of these classic tests of general relativity. So the earliest success, one of the earliest successes of general relativity is the precession of the perihelion of Mercury.